So I want to resume where we left things off yesterday. So I didn't quite get to the end of the construction that I was trying to do, but I was trying to convince you that we can use the UP operator to formulate a reasonable way of breaking down the space over convergent modular forms for a fixed weight, which will give us some idea of how to construct the eigencurve. So in this setup, we were doing some p-adic analysis. So from yesterday, k was an integer weight, and we were working with m. We are going to do this abstractly, but we are thinking of the space of over convergent forms of some fixed radius. And we said that this is an orthonormalizable Banach space. So we're thinking of having some EIs as an orthonormal basis. And we have our choice of operator over the space, UP, that we said is compact. Great. So remember that by compact operator, we mean that if I take this operator and I can see it as a limit of finite rank operators inside the space of homomorphisms from M itself, what we can attach to this is something called the Fredholm series. So this generalizes the notion of characteristic polynomial in this setup. So what is the Fredholm series? I'm going to write it as phi x. So this is often written as determinant of 1 minus x phi. I'll put this between quotes because it's not a literal definition, although if I were to start with a finite dimensional vector space, yes, this does coincide with the algebraic definition. So how is this defined? So this basis that is not necessarily finite, of course, but maybe we want to think of this being countable for simplicity. I'm going to define the series by defining certain coefficients. So this is going to be an infinite sum. So I'm going to denote C0, I'm going to define it to be 0. And the coefficients Cn's are going to be given a series as well, where this is going to run over the sets of size n, where S is a subset of I for my orthonormal basis of CS. And now I'm going to tell you what CS is. Well, this is going to be the sum over, this is going to now look like a determinant, more or less, sigma in permutation of S of the product, sine sigma of the product over I of AI sigma I. Yes, okay. So first claim is that this makes sense, meaning that this is an infinite sum. We're claiming that it converges. If you think about what the term C1 is, this is more or less what you would imagine being, sorry, what is a I sigma I, and this is Aij is I'm thinking of this as an infinite matrix, as I and j are in I, that represents phi. Okay, so the first claim is this makes sense, so this is finite, that's okay. This converges, so for example, the trace of this infinite matrix converges using the fact that the UP operator is compact. And moreover, this is actually quite a nice series because we can say that another consequence of the compactness is that this lies in K double curly bracket X, which is the ring of functions. What is K? K is QP in my setup, base field. And this is the ring of functions of A1. So, which means that in practice, whatever value I choose for this variable, this whole thing converges, which means that the coefficients have to decay pretty quickly. Everywhere convergent power series, that's right. That's exactly what it means. So it turns out that if I now allow myself to work over CP, it turns out that such a power series, where I'm noting that by definition the coefficient C0 is 1, this is important, actually can be written as some sort of infinite product of polynomials. I'll insist to write them so that the first coefficient, the constant coefficient, is equal to 1. Where, maybe different letter here, maybe K, where, well, if I write it that way, alpha K better be the inverse of a 0 of this. With some exponent. So, yes. Sorry, yes. S is the subset of I. Hmm? Yeah. Mm-hmm. Thank you. So, in fact, one can prove this type of result as a consequence of Weierstrass preparation theorem that you can apply to disks of bigger and bigger radius. And in fact, this is exactly what we need to think about when we try to split up this power series into a product of a polynomial times another infinite series. So I'm gonna, if I take H in Q, I can look at this power series restricted to the disk of corresponding to points of valuation at most minus h, and I can look at the zeros inside that will be most finitely many, and I'm going to use this to construct a factorization of this. So I'm going to write this as a product of, I'm going to write it as fx less than or equal to h times fx greater than h. So this guy here is a polynomial for simplicity of notation, maybe I'll write this as q. q of 0 is equal to 1, so constant coefficient 1 for both of these guys, right? So the big input that we are now going to use, once we have this factorization, we want to get a decomposition, a corresponding decomposition of this guy here. So in order to do that, we appeal to a result that I think is usually referred to as risk theory. This produces a decomposition of M as two pieces, each correspond to a piece of a factorization. Such that they satisfy the following properties. Oh no. Okay. What is that? I can define this piece of that should correspond, we should think of that as slope less than or equal to h as, I'm going to do the following. So I'm going to denote this is going to be the kernel of Q star phi. So here, just as a warning, there is a lot of playing around between phi and its inverse wherever it makes sense to take its inverse, and the same with the zeros of the polynomials, because we are writing the series in terms of reciprocals. So it's a little confusing, but I'm hoping that this is correct. Q star x is going to be, evaluate q1 over x and multiply by the degree, x to the degree of q. And phi is going to act invertibly. So this is obviously going to tell you that this is 0 on this guy. Phi acts invertibly on it. With this being exactly its characteristic polynomial. And the other piece is a little harder to pin down, but this is going to be some canonical complement in which this is the important property. We have that this guy that we were taking the kernel of here is invertible on the other guy. Forgot to say the most important thing of all. This is finite dimensional. So here is really where the crux is. This is finite dimensional over k of dimension equal to the degree of the polynomial. So this is what we were after. We're looking for a way to break up the space of overconvergent modular symbols, which modular forms, okay? All right. We could have done that, but we didn't. We're doing this. So we found a way to break down the space of our convergent modular forms into a finite dimensional piece on which the UP operator acts invertibly, and in fact we can say what the slope is, bounded by. Here, now that we've done that, we weren't just after understanding the UP operator, we want to understand all the Hecke eigenvalues. So now that we have this finite dimensional piece, we want to consider more operators. So I'm going to consider T tilde is going to be an abstract Hecke algebra. It is the abstract Hecke algebra generated by Hecke operators TL, as L does not divide NP, diamond operators as D prime to this tame level, and very importantly, of course, UP. It turns out that, okay, this guy, so I'm thinking of this like as pretty much a ring of polynomials in infinitely many variables. That's fine. Hecke operators have a canonical definition on the spaces of modular forms by correspondence. I've now broken down the space, and I'm going to denote as T less than H the image of this abstract Hecke algebra inside this. This finite dimensional. It's not clear that this makes sense based on the way I constructed it. I constructed a composition that makes sense for UP. Fine. Is it clear that it goes well for that the two pieces are stable? So this is part of Ries's theory. It actually tells us that the projectors onto the two components are in the closure of the subring generated by this compact operator, and you can use this to conclude that if you started with a Hecke algebra of commutative operators, then everything is fine. So this actually makes sense. Great. So what is the upshot? If I fix a weight k, classical in the setting, I can do this construction, and I can now here I'm going to have a finite dimensional Hecke algebra. I can study its points. Its points are going to correspond to systems of Hecke eigenvalues. Great. I can vary H as H tends to infinity, and I should recover a lot of systems of Hecke eigenvalues, but not all, because H is always going to be finite in this construction. So structurally, we are going to miss all the systems of Hecke eigenvalues for which that might appear in the space of modular forms corresponding to M, such that the UP operator acts as 0, or more generally is not potent on that part. So we're not going to see any of that. Okay? So it's not too far from the truth that this is how the construction goes over the weight space, but there is a lot to do more carefully. But I think it's fair to say that there are some local pieces that look like what we have in this construction thus far. So, like I can think of what I've constructed as, okay, I can take my base field K, map it into the ring of polynomials in one variable, and okay, I'm going to map this variable into I'm going to look at, okay, let's call t less than or equal to h, this guy, and I'm going to map x to phi inverse. This makes sense on this piece, even though phi is not necessarily a variable in this sense, and factors through this qx. This is the picture that fiber-wise should generalize the idea of what we will get in with maps in the opposite direction for rigid spaces. This should be generalized to a local piece of the eigencurve. This is going to be a local piece of the spectral curve, and this is like going to be a local piece of the weight space. Okay? So let me just state a theorem. So here we're going to change weight space a little bit compared to what we discussed yesterday at the very beginning of the talk. We had assumed that we were working at tame level 1. We need to change that to allow level n. So I'm going to take W to denote what we might want to call Wn, which is this same construction as yesterday. I'm going to take spec of lambda n and take its rigid fiber, where lambda n is, again, a completed group ring, but I'm going to take zp star times what is going to account for the characters of conductor up to n, will parameterize essentially the Nabin type of the characters. It's not going to be super important. As we saw yesterday, already without this piece, this would break down, as a rigid space, would break down as a union of disks parameterized by the powers of the Teichmuller character. If I add this, there will be also a character of this group in the parameterization, but the idea is essentially the same. Now, huh? Yeah, thank you. Yes, completed group ring, like yesterday. Great. So I can say that the theorem, I'm going to say this is in a cheeky way, but the theorem of Coleman and Mazur is essentially that the above construction performed over W produces rigid analytic spaces with maps from C to Z to W, where I'm going to call C. Is that what I wanted to do? Okay. No. Which one is it? So C is what I'm going to call the eigencurve of tame level n. Z is the spectral curve, and the weight space we already know. So the local pieces of this guy will look exactly like what I've described just now. So the local pieces will be of the form, so W is going to be some affinoid in the weight space over which there is some module, this is that I'm going to call MV, quite mysteriously, which is over convergent modular forms over V. But I'm not actually going to give you the definition. Vincent promised that he was going to talk about this. So how to make sense of this space of modular forms for weights that are not the classical weights that we described yesterday, so they don't correspond to an integer weight k. But let's believe that one can do this and sort of do this in families as well. And then I will get over this. I will get some sort of decomposition of a Fredholm series, again for the operator corresponding to UP, factoring as a product of a polynomial. So this is going to take values in a generalized version of what I had before. This is going to be a polynomial which will produce a corresponding decomposition. I'm going to go Q. Plus whatever complement we're going to get. And this will give locally a diagram. So this guy will be a projective of the module of rank equal to the degree of the polynomial. Yes? What is H? Oh, yeah, so there is a lot of lies built into this way of presenting the whole thing. In practice, this construction is local, but not local on the basis. One first constructs a version of one first constructs the spectral curve, which is going to be given by this sort of Fredholm series that will be well defined everywhere. And then locally on the spectral curve in a little neighborhood of a point, you can find a decomposition like this by looking at the image of that neighborhood on the weight space, but you can hope to just factor the whole thing over the weight space. But so the idea of the whole thing is essentially, if you think of the eigencurve, this is going to be given by a space in which around the point, the structure on the eigencurve, the structure of the whole thing looks pretty reasonable. When you want to study global properties, that's a much more difficult question, okay? So this decomposition, with this decomposition in mind, you will, wrong piece of paper. Okay. You would produce something like we had before. So map from OV to OV. No, one x modulo of this Q. And then we're gonna go into this. Some T depending on V and depending on Q as well inside the endomorphisms of MV. Right, Q. Okay, so this is what gives you the local picture. Great, so what are we trying to do? So I stated that this generalizes what space did I construct at the end of the day. So the important point is, what are the points? How are we interpreting them? Should also say, did I say? Note, we call W the map from C to the weight space, and this is referred to as the weight map. And studying local properties of the weight map is quite important. What is the eigencurve doing for me? Well, if I can take its points, so I'm going to take a point inside here, and I can look at the fiber over this point. And I can interpret the points of this fiber as morphisms. The construction of this whole gadget is going to give me a morphism between this abstract Hecke algebra inside the ring of functions of the eigencurve. So that means that I can interpret points in here as, so if I have a map from this corresponding to a point, I'm going to interpret it as a system of eigenvalues for this abstract Hecke algebra. And what systems of eigenvalues do I get? So these are going to be exactly the systems of eigenvalues for the abstract algebra, such that this mysterious space of that should correspond to an arbitrary weight that we described in the case in which we can take an integral weight, appears in here. This is going to be the eigenspace correspondent to the system of eigenvalues. And by construction, the UP operator is not allowed to be 0. Okay? So we're seeing all the systems of Hecke eigenvalues appearing in here such that UP is non-zero. Okay? So next board, what are we going to do? I'm going to go here. So some properties that follow almost directly from the construction, plus the fact that we are working in a finite dimensional case because our weight space is finite dimensional, one dimensional. The weight space is one dimensional for us. This makes our life a little simpler when wanting to prove some geometric properties of the objects that arise. So one thing is that C and Z are curves, so they are the same dimension as the weight space, which is what one would expect in general. And the map W is locally finite and flat. Other property that is also not too hard to show in this case, if I take, let's say, let's call it U, an irreducible, that's not good notation, but we're going with that, an irreducible component, then I can look at the image of the weight map for this irreducible component, and that's going to be hit a component of the weight space. And the claim is it can miss at most finitely many points. In the corresponding component. Of the weight space. Okay? I should mention there was another important lie in what I just said. So earlier on I was carrying this parameter r, which denoted the radius of overconvergence, and at some point I dropped it and pretended like it was never there. It's a theorem that you can actually do this and get the same construction and glue things in a reasonable way by doing that. There is an interplay also between the choice of affinoid, where you can define this, and the radius of overconvergence, and lots of subtleties to consider about that. Okay? So these are properties that follow pretty much from the construction. What we haven't, and plus the one-dimensionality, we haven't actually said much about in what sense this whole thing interpolates systems of Hecke eigenvalues appearing in the spaces of classical modular forms, because yes, we said that the space that are constructed of overconvergent forms contains a space of classical forms, fine, but it's not clear at all that I haven't just generated like so many more eigensystems that I cannot find my original eigensystems anymore in whatever I've built. So that's one thing that we need to worry about now. And this brings me to the next topic, which is classical points. So before I get to classical points, I need to update what I mean by classical weights. In Wn. So this by definition is going to parameterize the characters of Zp star times Z mod and Z star. So I'm going to view those as a pair of characters. And I'm going to say that the weights that I call classical are of the form what I called classical weight yesterday, corresponding to the integers sending x to the k, and epsilon, a finite order character. I don't mind what this is. So I'm going to view those as a pair. Note that you might want to consider other classical weights as well, and it would make sense to consider also weights that factor through a finite quotient. Here, I'm not going to do that today, but it's worth doing. I'm going to stick with these because these are going to be enough for what I'm going to talk about. So what am I going to call classical points? Well, the classical points will have classical weights, but that's not going to be all. So I want the classical points to be the x points in CP value points such that the corresponding homomorphism from gives the systems of Hecke eigenvalues of this guy appears in the space of classical modular forms that for our purpose, I'm going to denote gamma as gamma 1n. Intersect gamma naught p. I'm going to say mk gamma. Classical space, what is k? So, yeah. The weight of x corresponds to the classical weight k epsilon. I don't need to worry as much about this epsilon, so I'm not going to include it in the definition here. This is because I'm including, this will have to do with the action of the diamond operators, and this will be encoded in the way one interprets this space of modular forms over this arbitrary base. Okay, so classical points are those such that the system of Hecke eigenvalues appears in classical modular forms of this level. So gamma 1n, and we are allowing also level at p. Okay. Oh, I can just write here. So the important thing that we want out of these points is actually that these points are dense in a sense. More precisely, they are Zariski dense. And in fact, very Zariski dense too. And in order to prove that, we are going to use a big hammer, which is Coleman's classicality theorem. So what is that? Coleman's classicality theorem. So this is really what makes the whole thing worthwhile here, that we didn't just construct a crazy space. So if H, here I keep thinking of this H as a slope and look back at the type of the composition that I was considering at the beginning of this lecture. If the slope is less than k minus 1, yes, then, well, in general, we said that we have an inclusion of the classical forms of this level inside the over converging ones. So this is going to be an inclusion. But if I restrict on both sides to the parts in which my slope is bounded by h, then this becomes an equality. Okay? So basically, what we want to keep in mind is if the slope is relatively small compared to the weight, then everything we produce with slope bounded by that is already classical. Great. So an important remark. So 0 is less than k minus 1 if k is at least 2. Important. This will come back tomorrow. So, and indeed, the case of h equals 0, meaning that the UP operator acts invariably, has been studied well before Coleman's theory, and this is what is called Hecke theory. So for h equals 0, this is a result of Hecke. Which, in fact, was obtained in a different language, we might say, and is not entirely, cannot entirely be viewed as a consequence of Coleman's theory. So there is an overlap between the two things, but Hecke theory is more precise in the sense that tells us about integral results as well, not just about rigid spaces. But an important consequence of this, of Hecke theory, is that in fact, if I look at this part of slope of the, I'm going to denote this as the slope less than or equal to 0 or equals 0 on the eigencurve. This is also called the ordinary part, often. The map from this part to the weight space is finite flat. This has important consequences when we try to draw a little picture where what we imagine our eigencurve to look like, because this tells us that there is a part of the eigencurve. So now I'm going to draw the disks as lines, which is a little weird, but we're going with this. This should correspond to components of the weight space. And over the, our eigencurve, maybe we want to think of sort of the slope increasing in this direction. Over the part of slope 0, we'll have a few components that are nice and slope 0 across. Then things might get a lot more complicated elsewhere. We don't know. One thing we do know, and this happens on all components, what are the points that we are missing for each component into when we map onto the weight space? We might miss a few points. Those points arise from the fact that when we write down our Fredholm series, in general, we will have some coefficients that are given by functions over affinoids on the weight space. And those functions might have some simultaneous zeros. And if those are simultaneous 0, it means that the Fredholm series at a point is just 1, which means that at that point, for the piece that I had written down, I am not getting any finite slope eigenforms. That's okay. Yeah. Mm-hmm. Sorry? Yeah, I think so. Okay. Also worth mentioning that recent results on the geometry of eigencurves actually tell us that when we go closer to the boundary of the weight space, this picture becomes simpler. So, but we are not going to do much with that for today. So, but we should really keep in mind that the integrate behavior might arise towards the center. And in particular, it will not be so clear if all the families have finite degrees or not. There are a lot of questions that are still not understood. Right. So did I state what I meant to state? Right. So yes, the punchline was we can use Coleman's classicality theorem to conclude that classical points, as I've defined them, are Zariski dense. In fact, as I said, there are what is called very Zariski dense, which means that if I, not only they are Zariski dense, but if I take a point and I look at it, I can find the bases of open affinoids around it, and the classical point will still be Zariski dense inside it. So the idea for this is actually pretty simple, but this might be one of the things that we discussed in the discussion session, and if you want to get into more detail, is that simply, like, if I take K, the classical weight, well, I can find, as I mentioned, want to look at every irreducible components and check that my classical points are very Zariski dense inside it. I'm going to look at the map to the weight space. That map is going to miss at most finitely many points, so it will contain some classical weight, inevitably. But when I have a classical weight that I can find more classical weights, I can find the sequence Kn given by K plus p minus 1 p to the n. So this will converge to the classical weight K p-adically. That's fine. But also, the point over the classical weight will have a certain slope, and at some point will break the bound given by Coleman's classicality theorem. And then from that point on, all of those points are actually going to be classical points. So this is something that we can maybe flesh out in more detail later. Another consequence of this is that actually, using that theorem, we can conclude that with a relatively simple argument that the eigencurve is reduced. So what we need to understand in order to say that this eigencurve is reduced is that we want to apply a criterion of Chenevier. That is actually not that difficult to show, that if we can find infinitely, like Zariski dense set of points, such that I look at the corresponding, look at those points, and I look at the corresponding system of Hecke eigenvalues. If I can find that the action of the Hecke algebra on that system of Hecke eigenvalues is semi-simple, then I have reducedness. So this is related to semi-simplicity of Hecke action, which can be described concretely for the points such that the Hecke algebra acts via a classical quotient. So let me spell this out because it's going to be important later. So first we need to understand what eigenspaces versus generalized eigenspaces are in this world. So I'm going to take x, a classical point, the weight of x is going to be the pair K epsilon. And for this point, I will have a system of Hecke eigenvalues. Then, because I know that this, by definition, this is a classical point, so it comes from classical modular forms of level gamma. And I have this eigenspace attached to the system of Hecke eigenvalues here that is non-zero. This will fit inside the generalized eigenspace that I'll denote like this. So I'm going to look at this inside the overconvergent forms. And this double bar here is a notation that means concretely, I'm going to take this space weight K and localize the prime ideal corresponding to the system of Hecke eigenvalues defined by this guy. In practice, this means take all the generalized eigenvectors for the system of Hecke eigenvalues. So a priori, we don't know how the two compare, and this is going to be the big theme that we're going to explore in the lecture tomorrow. But importantly, if I assume that H is less than K minus 1, which I can do for a Zariski dense set of points, as I just hinted at, then this generalized eigenspace is going to be a classical generalized eigenspace. So if I can say something meaningful about that, then I can just conclude. So I can force this eigenspace with some simplifying assumptions. I'm gonna assume that x corresponds to a classical form, which it must in a way, of thing level n meaning that the prime to p part of the level is n, by which I mean it doesn't actually come from lower level away from p, away from p, that's what I mean to say. This is just a simplification, but the idea works anyway, and assume that f is a cusp form, again for simplicity. Then I want to conclude that this space is actually one-dimensional under quite reasonable assumptions. So I'm going to look at the action of the Hecke operators away from P and at P. So if I look at the Hecke algebra, so Hecke operators dl for L not dividing NP and D for D co-prime to N act semi-simply. This is not hard to show. This is because this, you can use the Peterson product on the space, the classical space of modular forms, and these operators in the setup, as I'm taking L to not divide the level, are normal, which implies that the action is semi-simple. We need to worry instead about the UP operator. So for UP, it's a different story, and we need to consider two cases. In my setup, I'm fixing the fact that the tame level is n, but I can't really expect to fix the level at P. So I generally have two possibilities. So I'm going to continue with this. For UP, I have case 1. F is P nu, which means great. We actually don't even need UP to single out this eigenspace. But for the record, I'm just going to say that I can actually say explicitly what the slope of UP is going to be in this case, which I hope I wrote correctly in my notes. So this arises, the point of saying this is a very specific slope case. But this does not cause any problems to us. The problem can arise from old forms. So if F is P old, so this means that it comes from a form of level gamma 1n. Then how can it be an eigenform? So the eigenforms are produced by the following recipe. So F will have to be of the form G alpha, meaning where alpha is the UP eigenvalue. So alpha is lambda x of UP. And this denotes the unique stabilization of this form, or G of level gamma 1n. And this denotes the unique stabilization of that with eigenvalue alpha for UP. Okay, but what is alpha? Alpha is detected by the roots of the Hecke polynomial x squared minus apx plus epsilon p to the k minus 1. equals, this will be factored as a product, x minus alpha, x minus beta. So the only way for this to not be semi-simple is that the root here is repeated. So I can rule that out by demanding that. So I'm going to say, just going to introduce notation because it will come back. So I'm going to say that if alpha equals beta, then I call G, G the old form, then G is called irregular. And if alpha is not beta, then G is called regular. Right, so how can I make sure that if I want UP to act semi-simply, I want to be in this case, to guarantee this condition without worrying too much about it, I can ask that I want to take H fix a slope that is not what it would be if I had a repeated root k minus 1 over 2. Then inevitably I'm in the regular setting. So there is only one possibility for it to be a risky setting. So I can massage the same argument that I provided, that I suggested before to prove the risky density of classical points, to say that in fact I can find a risky dense set of points such that this condition is also verified, but great, that implies that the eigencurve is reduced. I should also point out this condition is not expected to, the irregular case is not expected to happen at all if k is not 1. So this shouldn't happen. If k is not 1. And I want to say a few more things to set myself up for tomorrow. So another consequence of this density statement is that actually was I numbering things? I don't remember. So if I take x, a point in C, a point of the eigencurve, then there exists a unique two-dimensional Galois representation corresponding a unique two-dimensional Galois, semi-simple Galois representation that corresponds to this guy. Characterized by the property that this is unramified for Primes L not divided NP, and let's say the determinant of this representation can be explained in terms of is related to the weight of X and can be described explicitly. And let me say what the trace of this representation is. And this is going to be given by so when I evaluate at a Frobenius at L, then I take the trace evaluated of Frobenius at L and get the system of eigenvalues corresponding to X evaluated at TL. So this construction is not actually a construction of a Galois representation over the eigencurve. There is an intermediate step that requires constructing what is called the pseudo-representation by interpolating the classical representations corresponding to the classical points of the eigencurve. What is a pseudo-representation? We can think of it as something that interpolates the characteristic polynomials take a representation and evaluate at the various elements. So in fact, for a two-dimensional case and in characteristic not 2, it's fine to just interpolate the trace, and that would be enough. So this point of view of Galois representation is actually quite important, and it will be the center of the discussion tomorrow. Let me just conclude to introducing the topic of studying the local geometry of the eigencurve, which is around classical points. You can have various reasons to want to understand that, but some possible reasons that you might be interested in are either in the realm of p-adical functions. You might want to, for example, interpolate cohomology classes around certain classical weights. Or if you're thinking of the point of view of more Kudla program style, you might want to find interesting families in which you can maybe say something concrete about derivatives around a classical point. So we're going to say a little bit of both tomorrow. But let me conclude with what we know. So the local geometry at classical points So an easy observation is if the weight map is étal at X, then this tells me that the eigencurve is smooth at X. The converse might not hold. For example, I can imagine a picture which X is this. This is the classic picture of smooth but not étal. Okay? A way of detecting this smoothness or étalness is the following. We look again at the overconvergent generalized eigenspaces. And under the assumptions that I stated before, which can be massaged, but just for concreteness. So let's say if I'm taking X, a classical point, that corresponds to corresponding to a cusp form of level exactly n and not tame level, sorry. Level exactly n. Then I can interpret etalness entirely in terms of the generalized eigenspace and say that I look at the overconvergent generalized eigenspace. This is one-dimensional if and only if W is étal at X. In general, I will have to be a bit more precise here. I probably want to say that the correct statement would be this corresponds to the classical space because I can have a bigger space of eigenvectors, but there is also something to worry about in terms of levels. But okay, so this is the picture. And so from the discussion that we just did, the conclusion is if I do the same thing as before, and I put myself in the case in which h, the slope, so the p-adic valuation of lambda u x, lambda x u p is less than k minus 1, and I'm in the regular setting, and the corresponding, and x corresponds to g and regular form, then the wave map is étal at X. The story becomes quite interesting when I'll just make a conclusive remark. And the story becomes quite interesting if I look at the case in which the slope is equal to k minus 1. So for classical points, note that we either have the deform is p old, or in the p new case, the roots appearing here have sum of valuations equal to this product here, so k minus 1. So the valuation can be, for one of the roots, can be at most k minus 1. So that's really the boundary case. Then the picture becomes quite interesting. And in fact, what we can say about this is that the eigencurve may or may not be étal at those points, but that property is characterized entirely in terms of the corresponding Galois representation when I restrict it to the decomposition group at P. This is a result that requires a lot of different pieces and links to the theta operator that Vincent said something about yesterday, and I'm happy to discuss this further with whoever is interested. Just want to say, this discussion today was empty in the case in which the weight was 1. So there isn't a case in which the slope is less than k minus 1 to consider. And this additional condition of p regularity may also fail in that case. On the other hand, that's a very interesting case because that's the one that has the most bearing with like concrete arithmetic of number fields, because the Galois representations corresponding to the points of weight 1 are RT representations. So they have finite image, and they can be used in some cases to say something that has the flavor of some sort of explicit classical theory. And I'll stop here.
Does it work? Yes. Do you have quick questions for each? If so, I'll bring the microphone.
Maybe this is very naive, but for those representations, when they're not the RAM at P, are they supposed to correspond to something, I don't know, something like another object? Or
So they are...
when they're not the RAM at P?
So they're not the RAM at P, right? In general, the correct notion of P will be expressed in terms of, again, p-adic Hodge theory, but it would be called triangulin. They should correspond to... I think it's hard to say something particularly concrete about those points in the eigencurve, but there is... The conditions at P have been studied intensely